In last lecture, we have already discussed about many details about the piles, single piles under the lateral loading to calculate the ultimate resistance, including the ultimate horizontal force and the ultimate moment for single pile, right? And we talk about several keywords, the short pile or long pile, and free head and fixed head. Also, what is the type of the soil surrounding, right? So as you can see, the short pile, we regarded it as a rigid pile. Okay, it can only rotate. It has no deformation by itself. Okay, but for the long pile, we can say it is a flexible pile. And at the pile body, for example, here, under a large horizontal force, a plastic hinge might occur. Okay, so that for the long pile, the failure is controlled by the pile body itself. Okay, and for the short pile, because the pile itself is rigid, so the failure is controlled by the soil. Okay, this is the main difference between the short pile and the long pile failure mechanism. So for the long pile, because it is infinitely long, okay, infinitely long, so we can say that the resistance from the soil is infinitely large, so that the pile will fail earlier, okay, than the surrounding soil. So you can see here the fixed head and the free head, right? And normally we will use the free head to do the calculation and do the design, because fixed head is very difficult to achieve in the real construction. So free head design is more conservative and more on the safe side. And we discuss about the clay and sand. Okay, we discuss in quite detail why for clay we will assume the friction angle is equal to 0. We only consider the cohesion, the Cu, okay? And for sand, we would normally consider about the passive earth pressure, okay? And for clay, actually, for today's new lecture, in lecture 3, the sloped soil nail, the soil nail slope, okay? We will also see sometimes we will use this assumption, the phi is equal to 0, and sometimes we will use the real phi value. Okay, let's see. So which condition we will use different assumptions. So for this one, I keep it here for helping you understand. Okay, understand why we will have different factor for calculating the bearing capacity, the failure stress of the soil. So all the following slide actually shows you the many equations to calculate the ultimate sorry. Today I don't know why I set a different setting here. I need to admit for some students, okay? And so the following slide actually is for showing you the different equations for calculating the ultimate moment and ultimate horizontal force. Okay, as I explained today in the tutorial, for deriving these equations, we normally would do the same thing. Okay, we cut it here. You see, we cut it here. Okay, this position is the maximum moment happen. Okay, at this position. Okay, we cut it. And then we consider about the horizontal force equilibrium. Okay, we can take this section for this equilibrium checking, and we can take the bottom section for the equilibrium checking. Okay, we can establish the equation and cut it. After cut it, we normally will take moment at this cutting point on the pile. Okay, take a moment here. Then we will establish another mi. Okay, summation is equal to 0. So the equilibrium of moment. Similarly, we can check this part and also this part, the equilibrium of moment, and then establish new equations. Of course, we have different conditions. For example, this one, we will take a moment at this point because we want to avoid to get this P involved. Okay, to get this P involved. So we will take a moment at this point to establish the equation. And so here I also present you some supplementary information here to help you to understand why we will have a 3 here, okay? Why we have a 3 here for calculating the shear strength for the sand, okay? For example, because previously you learned this one, okay? You learned this one before, but now actually we are more, because this is pile, okay? The soil condition is more like a 3D condition, so that we will have a 3 here because we will have larger failure surface, and the resistance from the soil to the pile will be larger. Okay, so case is different with retaining wall case. So, okay, this is a free head and fixed head, and we do the same thing, the cutting and the equilibrium of force and moment to establish the equations, all right? And for the free head, you should be careful about here. Okay, we have only 1 MU because we only have 1 plastic hinge here. But for the fixed head, actually we have 2 here because we have 2 plastic hinge. These two are the same, the value, I mean the same, because it has a fixed head on the top. So for the example 4, we have already discussed in the lecture, in the tutorial this morning. Lecture 4, including this one, okay? And okay, so for all the examples, we have for all the example from 1 to 4, okay, we already discussed. And at the last section, we discussed about how to determine the pile horizontal deflection under lateral loading, right? So for this part, we just use the so-called subgrade reaction method, okay? In this method, we assume the soil is like a spring, okay? It's like a spring, okay? And this method actually is proposed by Winkler, okay, many years ago. And in his assumption, not only to assume the soil is spring, and he also assumed there is no interaction between each 2 springs. Okay, there is no interaction. So this is his assumption. So that if we assume the soil is like a spring, we will have a factor just like the spring factor, right? The elastic modulus, like for the spring, like here we give a name, the coefficient of horizontal subgrade reaction, right? And the coefficient, okay? Be careful, here is coefficient. Later we introduce a new parameter called constant. Constant means the value will not change, right? And the constant of horizontal subgrade reaction. Normally this one is more commonly used, okay? This one is more commonly used in the design code, okay? We will discuss a little bit more later. So you will see that the KH, the so-called coefficient, actually when we assume n value is equal to 1, the KH multiplied D is equal to NH multiplied Z. Z is the depth, right? And D is the pile diameter or width. So this one, we can imagine that if this value NH is a constant, so the KH multiplied D will become larger with the depth, right? This one will become larger with the depth, which means the stiffness of the soil, actually, it implies the stiffness of the soil keep increasing with the depth. Okay, this is a deflection. So this one you can just regard it as some kind of stiffness parameter. Okay, it will increase with the depth. Okay, this is very common. And multiply the delta H, the deflection, we can calculate the force. Okay, as I discussed with you, this force actually is a line load. Okay, a line load. This line load is, you can see here, per meter, right? This meter means the pile length. Okay, the pile length. The force per unit length of pile, how much is it? Okay, it is represented by this p-value, this p. Okay, so we have a per meter here. This means the pile length. Okay, we will have a very similar definition today for the slope. Okay, we can see later. So as I said, the NH is more commonly used. Okay, you can see here. In the design code of Hong Kong, you can see for the dry or moist sand, the NH is listed here. Okay, it keeps increasing with the increase of density, from loose to dense. The NH value will keep increasing. Okay, the density actually can be defined by this dr. Okay, the relative density. This is more scientific concept about the density. Okay, here you learned it before in the soil mechanics, right? And this researcher gives this relationship between NH and dr. Okay, very direct and simple relationship. We can directly to use for sand. Okay, this is for sand. So with the increase of the saturation degree, or we can say with the increase of the water content from dry or moist to submerged, okay, we also can say maybe it's saturated. Okay, so with the increase of the saturation degree, the NH, you can see, becomes smaller, right? Becomes smaller. All of them become smaller. This implies that the water, okay, normally is a very dangerous thing, okay, for the safety of the geotechnical structure. Okay, for example, if the water content keep increasing, maybe the sand is more prone to have the liquefaction, and the sand, the bonding between the soil particle will be weakened, right? Many catastrophe, okay, result is induced by the increase of water. Okay, like the heavy rain season, right? We will have more slope slide in Hong Kong. Okay, so with the increase of the water, the NH keep decreasing. You can see here, and here I just repeat this table here, and the NH can also be related to the horizontal Young's modulus. Okay, horizontal Young's modulus with this range. Okay, normally this Young's modulus can be measured by the in-field measured equipment like SPT or some CPT, if it equipped with the horizontal force load cell. Okay, so it can measure this value. And so this is for determining the NH according to the design code in Hong Kong. Okay, we also discussed this part for design chart method. Okay, design chart method, how to determine the deflection along the depth under moment on the top or under the horizontal force on the top. Okay, this design chart is very easy to use. One very important thing is this T. Okay, this T. Okay, we just jump to the last slide. Okay, this slide actually I get it from the design code directly. This T in the design code we have a name for it, pile stiffness factor. Okay, pile stiffness factor. For pile stiffness factor, this name for me is not that straightforward. I prefer to call it like a characteristic factor for this pile. Okay, so characteristic factor, the meaning of this so-called characteristic is because this factor is determined. Okay, you can see is determined by the Young's modulus of the pile and the initial moment, okay, of the pile. And NH represents the stiffness or the soil condition for the surrounding soil, right? So actually this T parameter considers the property of the pile and the property of surrounding soil. So for each pair of soil and pile, which means the condition has been fixed, okay, we will have one corresponding T. Okay, so I prefer just to call it characteristic factor okay? Because if you know the condition of the pile, because you know the diameter, you know the material of the pile, and we can also know the property of the soil surrounding, so that this T value can be easily determined, right? So here in the design code, actually, we have another very similar factor, R, okay? This R and T actually is just the two different symbols for two different conditions. R is for the constant soil modulus with steps, okay? In the example, we have confronted many conditions. We just assume this G average is equal to GE, right? It means no shear modulus change with the increase of depth of the pile. So it's very like this condition here. The constant soil modulus with depth. For example, the soil can be the stiff over-consolidated clay, okay, over-consolidated and very stiff, okay? For this kind of soil, the depth, or we can say that the self-weight, okay, will not change the behavior of the clay of this kind of soil significantly or obviously, okay? So that we can just assume this soil is uniform along the depth in the vertical direction, okay? So that we can make this assumption, the constant soil modulus with depth, because this soil is over-consolidated, okay? It has been experienced a very high pre-consolidation stress, okay? So that the current self-weight of the soil doesn't affect the soil behavior, obviously. Okay, so for this T value, so for this T, okay, it is for the soil modulus increase linearly with depth. Okay, this is more easily understandable, right? Because the soil will be compressed more into more larger degree under a larger self-weight, right? If we plot the self-weight curve, it will keep increasing, right? Gamma H. With the increase of H or gamma Z, okay? With the increase of H or Z, the sigma V, okay? The vertical stress due to the self-weight will keep increasing, okay? So the soil will become more stiffer, so the soil modulus keep increasing, okay? So this is for the normally consolidated clay or granular soil. Especially for the granular soil, if the granular soil, we write the Mohr Coulomb failure envelope, it is equal to C plus sigma n, okay, tangent phi, right? Tangent phi. So this tau or shear strength of granular soil very much depends on this value, sigma n, right? Sigma n actually, you can regard it as a sigma v, okay, the horizontal, no, the vertical, here, the normal, okay, the normal stress. Phi is constant. C, normally for the granular soil, we regard it as 0, right? So for granular soil, okay, very much depends on the sigma n. Okay, here I also present you the equations for calculating the inertia of moment. So how to calculate? You should learn it before, okay, in the structure mechanics, I guess. So here just present you to help you to directly refer to and do the calculation. And here, I think it's very important. Some student will ask, okay, we discuss about the short pile and the long pile. Okay, so what is the short pile? How to differentiate the short pile with long pile? Okay, so here the design code gives you the criteria. Okay, you can see when the L, the embedded length of the pile, is smaller or equal than 2t. Okay, 2 times of the characteristic factor. Okay, we can regard the pile as a short pile. But for the L larger or equal than the 4t, okay, 4 times of the t, it can be regarded as a long pile. Okay, similarly, when we use R, okay, for the constant soil modulus with depth, condition, we will use, okay, this one will be different. When L is larger than 3.5 times of R, the pile can be regarded as a long pile. Okay, we can also say it can be regarded as a flexible pile. Okay, so this is a definition or criteria given in the design code for differentiation between short pile and the long pile. Okay, here I discussed in quite detail about this T, all these R. Okay, actually, here in this design chart method, we use the T here to compare as a characteristic factor. Okay, we call it characteristic. It's more straightforward. And you can see, okay, we discussed this already, EPIP, bending stiffness of the pile. And this is about this. NH is for the subgrade, or we can say it is for the soil reaction, right? And I don't go to detail about how to use this chart, okay? How to use this chart. We should be, okay, the formula is here, okay, at the right bottom corner, okay, the formula is here. The value we get from this chart is just for this F delta, for example, this F delta, okay, because the remaining thing we all know, okay, with this F delta value, we can calculate delta H, or delta H means the delta due to H, okay, this here, the delta due to the moment, okay. So we only discussed about the single pile under the lateral loading. Okay, so far. For the pile group settlement using this rigid cap assumption, okay, if you should still remember, we discussed this already under the vertical loading, or if we have the moment on top, okay. This is for pile group. And now we discuss how to consider the pile group under horizontal force or horizontal moment and moment, okay? Horizontal loading, okay, and moment. And in the design code, it gives us a very simple method to consider the pile group effect. So we will have a so-called reduction factor, okay? Reduction means become smaller, right? So you can see the Rn value, the reduction factor, is always smaller than 1. Okay, you can see with the increase of the pile spacing, the distance between two piles, the reduction factor will become larger, right? Will become larger, and will become larger. So we can imagine that, or we can estimate that with the pile spacing, okay, over pile diameter. This is a ratio, okay? This is a ratio. This is a ratio. With the ratio becomes larger than 8, actually, we can assume there is no interaction between two piles because the reduction factor has already reached 1, right? Have already reached 1. So if two pile is more close, we need to reduct more, okay, for the soil reaction, which means we will have larger horizontal deflection, okay? So this equation we have already discussed. P is equal to NH multiply Z, then multiply delta H, right? Delta H. Soil reaction per unit length of pile, okay? The constant, the depth, the lateral deflection. Okay, so we can conclude that with the NH reduced, the deflection will increase under the same lateral loading. Okay, so more settlement or deflection for pile group due to the interaction. So the pile group interaction under the vertical loading or under the moment, we already know that from the example 4 or example 3b. Okay, example 3b. The settlement for the pile group is much larger than the settlement of single pile, even the average loading are the same. Okay, so here again to remind you that the pile group actually is an adverse effect for the settlement and the deflection of pile design in the pile design. Okay, and okay, here, even though this method seems quite simple, okay, it's widely used already and can generally produce an approximate result. Okay, in another way, we have a second method, okay, the so-called second method. The first one is just using this table, and the second method here actually is another figure method or design chart method, okay? But to determine these two curves, okay, is quite time consuming and quite expensive. Let's see. So with these two curves actually represent you the lateral loading, a lateral deflection with the lateral loading. Okay, you can see the first one, the top one is for single pile. The second one is for pile group. Okay, under the same level of lateral loading, the delta pile group is larger than the delta single pile, right? We have two delta. This is pile group, this is single pile. So with under the same level of lateral loading, the delta pile group is larger. Let's change to another perspective. Under the same lateral, with the same lateral deflection value or amplitude, we only need a smaller, okay? We need a smaller force for pile group compared with the force for single pile, right? Single pile. So we just look at this question from two different perspectives, okay? To show you that the pile group interaction effect, okay, will enlarge the pile settlement or pile horizontal deflection, okay? But how to determine these two curves, okay? We should do the real in-field test to under a lateral force and do the recording so that we can plot these two curves, okay? So that, I mean, I just said this second method, the figure method actually is time consuming and it will take a lot of money. So this is not very commonly used. Okay, so far we have already finished all the content in the lecture 2. Okay, do you have any questions so far? Okay, for lecture 2, I will suggest you to go through the example 1 to example 3b, okay, carefully about how to calculate and how to use all the equations and the definition and the concept of these equations, okay? Okay, how to consider the condition with a moment, okay, with a moment. In the assignment, you will face a more complicated condition. The force, the vertical force, and the moment are applied at the same time, okay? Okay, at the same time. So how to consider that condition? So we may have a brief discussion in the next tutorial. All right, so this is for the lecture 2. We already finished. Okay, so I have already uploaded the lecture note for lecture 3. So maybe let's move to lecture 3 now. Okay, I guess you can see the lecture 3 note. Okay, so for lecture 3, we are going to discuss the soil nail slope. Okay, because the volume of this lecture is quite large, so I divided it into 2 parts. And for this soil nail slope, some material might be repeated with your what you learned in the advanced in the geotechnical design, or even in the soil mechanics. Okay, but here we introduce the soil nail, and we will introduce the translational slip of the slope, and many other new concepts. Okay, some are new and some are repeated. Okay, to make sure the logic is quite clear, so we will also to help you to recall some memory about the concept in geotechnical design. Okay, so we will keep it here and we will discuss it here. So to keep it more in a more clear logic. Okay, so in this lecture, okay, the learning outcome you can see here for the part 1 is to determine the factor of safety. Okay, all of them are factor of safety. Okay, so for the slope, actually, this is the most important concept. Based on the total stress approach, for the total stress, phi is equal to 0. Okay, phi is equal to 0. And for the effective stress approach, okay, phi is not equal to 0. So we should consider the effective stress principle. Okay, effective stress principle. And for the plane translational slip with several special cases. Okay, the water table position and even the seepage force. Okay, and the slope with soil nail installed. Okay, this one is important. And how to use Jimbo's simplified method to consider the slope with soil nail installed. Okay, the soil nail sometimes is it has two or three or even many. Okay, so the number of soil nail can be varied. So this is a learning outcome for the part 1. And so as you may know, there are several typical types of slope failure. Okay, the first one is circular. Okay, circular means the failure surface of the slope. All we can say is this part is soil mass. Okay, a rotation soil mass, the rotation soil mass. In between, we will have a failure surface between this mass and the ground. Okay, and the failure surface here is, we assume it as a circular shape. Okay, so we will have one rotation center at each or any point on this surface. The distance between it and the rotation center is always equal to r. Okay, they are the same. Okay, this is a very important simplification here. So we can do very, simplified calculation to determine the factor of safety. Okay, so this is a condition for circular slip. And the second one is non-circular. Okay, non-circular. So this shape is not circular anymore, but it is curved. Okay, it has some kind of curve here. Okay, and the third one is called the translational slip, or we can say it's plane translational slip. This condition actually is quite common in Hong Kong, because in Hong Kong, the bedrock, okay, or we can say the bedrock or some stiff rock material is very shallow. Okay, it's very shallow, so that the soil on the surface, like the deposited soil on the surface, will present this kind of configuration. Okay, so it will slip along one direction, no rotation. Okay, slip along one direction. Okay, downward so we call it a plane translational slip. Okay, and the fourth one is compound slip. Okay, compound slip means a composition of different types of basic sleep. So you can see here is a it's more like the translational sleep, and here is more like a circular, or here is more like a non-circular sleep. Okay, this is more complicated cases. So in this lecture, as I mentioned to you, this factor, okay, of safety is most important. We use a lumped factor of safety to represent the condition of one specific slope.